Now student, we are going to discuss question number 5.7, and in this question it is given to you a bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. Clear? Now part number A, what is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment? Number 1, normal to field direction, second one, opposite to field direction. Clear? So let us try to understand this question. Let's suppose I am taking initially magnetic field in this direction, and let's suppose I am taking this initial magnetic field, or you can say uniform magnetic field. Clear? Now let's suppose I am taking here, this is a bar magnet. Clear? This is bar magnet, and let's suppose this is north and this one is south. Clear? And now if I am talking about direction of magnetic moment, this is also in this direction. So we can say initial position we are taking, this is 0. Clear? Now what will happen when I turn this bar magnet perpendicular to this magnetic field? Definitely we can say at the time theta 2 becomes 90 degree. Yes or no? When we place this bar magnet perpendicular to this magnetic field, from this direction we have angle 90 degree. Clear? So now you know, we can write here expression of potential energy. Potential energy we can write like this: mb cos of theta 2 minus cos of theta 1. Clear? So first let's suppose we want to turn this dipole from this side to perpendicular. So at that time I can write potential energy expression. This is given by mb. I can say this is cos of 90 minus I can say this is cos of 0. Clear? So value of cos 90 we have 0 and cos 0 equal to what? 1. Clear? So from here we can write like this: this is potential energy, this is given by minus mb. Yes or no? Cos 90 directly we can say this is 1. So what is amount of work done? So we can say total external work done, this is given by, directly we can say minus times of change in potential energy. Clear? Or we can say this is equal to plus times of mb. Clear? Now value of magnetic moment, it is given to you 1.5 multiply, what is value of b? B value is given, this is 0.22. Clear? So from here we can write like this: external work done. So W external, this one, it is given by 15 divided by 10 and multiply 22 divided by 100. Clear? So if you multiply you can say we have 30, this is 330 divided by 1000, and from here we can say 0.330 and this value we have joule. Clear? So from here we can write like this: external work done, this external work done is this one. Clear? Now let's suppose we want to move this dipole opposite to the direction of magnetic field, then what will happen? Clear? So concentrate here. If I simplify this expression, I can see now situation changes. Now this theta 1, we can say this theta 1 is already 0, this theta 1 is 0, but what about theta 2? Clear? We can say this theta 2 now becomes 180 degree. Clear to everyone? So in situation number B, or we can say part number 2, whenever we are changing this dipole in opposite direction, this theta 1 becomes theta 2 becomes 180. So here we can write this is 180. Clear? What is value of cos 180? Minus 1, minus 1 and minus 1, minus 2, we can write like this: this is plus times of twice of mb. Yes or no? Yes or no? This is minus 1 and minus 1, I can say this is minus of 2 mb. Clear? This one is minus times of 2 mb. Now we can write here external work done, this is equal to minus times of change in potential energy, I can see that is plus of twice of mb. Clear? It means we have to multiply it here 2 also. Clear? So we can write like this: this is 2 multiply this one, 2 multiply this one. Clear? So final answer we are getting, this is 0.66 joule. Clear? So we can say what is correct answer here? Correct answer we can say this is 0.660. 0.66 joule. Clear to everyone? Okay. Now what is torque acting on the magnet in case number first and case number 2? Clear? So we can easily calculate here, we can easily calculate value of torque that is acting. Clear? Now If we talk about situation number 1, in situation number 1 you can say torque, this is given by MB, I can say this is sin 90, clear. So from here we can say this is equal to MB, clear to you, and MB value we can say you can put here value of M, that is 1.5 multiply I can say 0.22, clear. So 15 divided by 10 multiply 22 divided by 100. So from here we can say this is 30, we have 330 divided by 1000, clear. So from here you can say this is 0.33 Newton meter, clear to everyone. So this one is a torque, this is acting over the part number 1. Now what is torque acting in this one, clear. So directly you can say yes, directly we can say here value of torque is given by MB sin of theta, clear. Now when I am changing position of a dipole from angle 0 to 180, it means I am writing like this, value of torque equal to MB sin of 180, yes or no, angle is now 180, now we know this is 0 Newton meter. So always keep in mind, whenever any dipole is situated either in a direction of magnetic field or in an opposite direction of magnetic field, you will always find net torque that is acting 0, but definitely we have to do some work if we are changing position of a dipole from stable equilibrium position to vertical or from stable equilibrium to unstable equilibrium, and clear, definitely you know total amount of work that is required, that is equal to plus times of 2 MB, clear, very important question. So this is all about this question.